Hello dolphins and welcome to the first wave flip notes with Miss Aquad. The first word we're going to talk about is a wave. A wave is a disturbance that transfers energy from one place to another without transferring matter. Let's imagine this. You have a beach ball on a lake. All of a sudden a wave is formed. The beach ball bounces up and down, but it's not transferred to the shore. Why is that? It's because waves transfer energy and not matter. Therefore, how are waves formed? Waves are formed if there's a disturbance in still water. If you take a look down below, you have two pictures. One is a picture of a wave or of water that has been disturbed and has caused a wave, and the other one is a transverse wave, which we will talk about in the upcoming slides. Our second word is medium. A medium is any substance that a wave moves through. So, for example, in the pond that we talked about in the first slide, the medium is water because the wave travels through the water. In a seismic wave, which is an earthquake, the medium is rock, dirt, road, or buildings, depending on what the wave is traveling through. So if you take a look at this picture, it is going through the ground. Therefore, your medium is the ground or the dirt and rocks. In this slide, we're going to talk about the two types of waves, not to be confused with the two wave movements. The two types of waves are mechanical and electromagnetic. In the next slides, we'll actually go through specifics about what is a mechanical wave and what is an electromagnetic wave. Let's start off by talking about our first type of wave. Our first type of wave is a mechanical wave. Basically, a mechanical wave is waves that transfer energy through matter. Mechanical waves have to have a medium. What is a medium? We said that the medium is any substance that a wave can travel through. Therefore, mechanical waves have to have a medium. Matter is anything that is made up of atoms. A mechanical wave moves energy through the matter, or a medium, but it does not actually move the medium, like we said in the previous slide. Sound waves, you can often hear things happening in the classroom next to us, even though there's matter, which is a wall, also known as a medium, in between. Rope waves also have a medium, which is the rope, and basically anything that is made up of matter and wave travels through is a mechanical wave. The second type of wave we're going to talk about is electromagnetic waves, also known as EM waves. These waves transfer energy through a field or empty space. These waves do not need a medium to travel. However, they can still travel through one if needed. So EM waves, even though they don't travel through a medium, they don't give away their energy like, for example, mechanical waves do. Therefore, they can travel forever, while mechanical waves cannot. The spectrum is a diagram of basically 7 different types of EM waves. If you take a look at the picture below, you will see it goes from radio waves all the way to gamma. Now that we have learned about the two types of waves, let's go through a comparison just to see what is the difference between mechanical and electromagnetic. There are 4 main things for mechanical. Number 1, it needs a medium. Number 2, it cannot travel forever. Number 3, it can move as either a transverse wave or a longitudinal/compressional wave, and we'll get into those in the next slides. Those are basically your wave movements. And then there are several types of mechanical waves. Electromagnetic waves do not need a medium. They can travel forever. They only move in a transverse fashion, and there's only 7 of them. Therefore, if it's not one of those 7, it's not an EM wave. We are now going to talk about the 2 wave movements. There are 2 wave movements. The first one is longitudinal, also known as compressional. You may use either one of these words to explain the movement. As you can see, right under the word longitudinal, there are 2 longitudinal waves. It looks a lot like a slinky going back and forth. That's basically what a longitudinal wave is. It's just a wave that goes back and forth. The next one is a transverse wave. A transverse wave actually goes perpendicular or up and down. So if you take a look above the word transverse, you'll see a transverse wave. Let's now talk about transverse wave in details. We said that transverse wave is a movement. It basically moves up and down or perpendicular to the direction in which the wave travels. There are two types of waves, mechanical and electromagnetic. Mechanical waves need a medium. Well, what mechanical waves move in a transverse fashion? Rope waves, the human waves found at sporting events, actual waves in the ocean. These are all mechanical transverse waves. The other type that we talked about was electromagnetic. All 7 electromagnetic waves move in a transverse fashion. Therefore, how do electromagnetic waves move? Transverse fashion. Do all mechanical waves move in a transverse fashion? No. But do all electromagnetic waves move in a transverse fashion? Yes. Now let's talk about the parts of a transverse wave. The easiest part of a transverse wave is the crest. The crest is the highest point or peak of a wave. The way that I like to remember this is when I look up into the sky, I see a crescent moon. Well, crest, crescent, sounds similar, right? Right. And where do you find the crescent moon? Up in the sky. Therefore, it is the highest point on the wave. The next part that we're going to talk about on a transverse wave is the trough. The trough is the opposite of the crest. If the crest is the highest point, then the trough is the lowest point. The way that I like to remember trough is that most animals eat or drink from a trough. And where is it found? On the ground. So therefore, where do you find the trough? It is the lowest point of the wave. In this slide, you will see the transverse wave, and you will see all of the crests and the troughs labeled. This is just so that you can see what it looks like. In the next 2 slides, we're going to be talking about properties of a transverse wave. The first property that we're going to talk about is amplitude. The amplitude is basically the point or the distance between the resting point, also known as the resting position, to the top of the crest, or the resting position to the bottom of the trough. Therefore, if you take a look at the picture, in the blue, you see blue lines. Those blue lines are your amplitudes. Therefore, the amplitude is from the middle of the wave to the top, or the middle of the wave to the bottom. It is not all the way from the top all the way to the bottom. It is a halfway point. Please make sure you understand that and don't draw the amplitude from the top to the very bottom. The next property we're going to talk about is wavelength. Wavelength is basically the distance from one crest to the next, or from one trough to the next trough. However, you cannot use wavelength from crest and trough. You either have to do crest to crest or trough to trough. So you must choose which one you're going to use, the top or the bottom. Now we're going to move on to the next wave movement. The second wave movement is a longitudinal or compressional wave. A longitudinal wave is basically a type of wave in which the disturbance moves in the same direction of the wave. Therefore, it basically moves back and forth. Longitudinal waves are normally vibrations. So what kind of items could we find in a longitudinal wave? Sound waves. A slinky can sometimes be a longitudinal wave. Therefore, longitudinal waves are mechanical because they have to have a medium. Now let's move on to the parts of a longitudinal wave. The first part that we're going to talk about is the compression. The compression is basically a region of increased pressure, the area where the wave is compressed or pushed together. So if you take a look at the picture, the areas where you see the dots are really, really close together. That is a compression. So think about it like this. If you compress something, you're pushing it together. So the areas where they are pushed together, those are your compressions. The next part of a longitudinal or compressional wave is the rarefaction. This is basically the region of decreased pressure, the area of the wave that is spread out. So we said that the area that is pushed together is called a compression. The area that is spread out is the rarefaction. So if you take a look at the picture in green, or the green arrow, you see the compression. Where you see the black arrow, that is your rarefaction, because that's the area that is spread out. Just like transverse waves, longitudinal waves also have properties. Well, one of the properties of a longitudinal wave is the same as the property of a transverse wave, which is amplitude. However, in a longitudinal wave, the amplitude is a little bit different in the fact that it shows how compressed the compression of a longitudinal wave is. So if you take a look at the pictures below, you actually have two pictures. We're going to start off with the one with the pitchfork. As you can see, the dots are a little bit more, the compression have dots that are a little bit more spread out. That is less amplitude because of the fact that it's not as tight together. If you take a look at the one underneath it, the dots are closer together. They are more compressed. So the more compressed it is, the higher the amplitude. The less compressed it is, the lower the amplitude. Now, if you take a look at the picture to the right, again, it's the same type of thing. There you see the black dots are not very compressed together. Therefore, you have a low amplitude, less compression, less energy. The one beneath it, the dots are very close together. Therefore, it has a greater amplitude, meaning that it has greater compression, higher pressure, and more energy. The second property of a longitudinal wave or a compressional wave is wavelength. Just like the wavelength in a transverse wave, the wavelength in a longitudinal or compressional wave is basically from one compression to the next compression, or one rarefaction to the next rarefaction, which is very similar to transverse wave where they did crest to crest and trough to trough. So again, you have to choose one. You can't use both. You either use compression to compression or rarefaction to rarefaction, and that's how you find wavelength. The next property that we're going to talk about is frequency. Frequency is actually used for both transverse and longitudinal wave movements. What is frequency? Frequency is basically the number of waves that pass a fixed point in a given amount of time. Usually it's about 1 second. So let's try to figure out what is the frequency for the two waves that we have. Let's start with the transverse wave. We have one of high frequency and one with low frequency. So if we're looking at the number of waves, we actually have to count the wavelength. So let's take a look at the first one. High frequency, 1, 2, 3, 4, 5 wavelengths. If I'm looking from crest to crest or trough to trough, I get 5 wavelengths. Therefore, what is the frequency for the high frequency transverse wave? 5. Let's now take a look at the low frequency wave. If you take a look at the low frequency wave, again, you look from crest to crest or trough to trough. So the first one, 1, 2. So low frequency is 2. Now let's take a look at a compressional or longitudinal wave. Again, this time instead of looking at crest, because longitudinal waves don't have crest, they have compressions and rarefactions. You can choose to either do compression to compression or rarefaction to rarefaction. So let's take a look at the first one. Let's look at the high frequency. You go 1, 2, 3, 4. So what is it? 4. Let's take a look now at the low frequency for the longitudinal wave. You have 1 and you have 2. So what is the frequency for the low frequency longitudinal wave? It's 2. I hope you enjoyed the slides and I hope you've learned something.